Hey, good morning. So today we will be discussing about mathematics in the Renaissance period. So introduction. Up to this time, the Italian merchants traveled widely throughout the East, bringing goods back in hopes of making a profit. Needed little by way of mathematics. Only the elementary needs of finance were required, so determination of costs and determination of revenues. Thus, they needed skills at financial capitalization, creation of instruments of credit, and generation of bills of exchange. So at the base of all this was the computation of interest. Needing more mathematics, they inspired the emergence of a new class of mathematician called Abacists, who wrote the text from which they taught the necessary mathematics to the sons of merchants in schools created for just this purpose. So they are uh, making words that are very needed or important in their merchants. So in the revenues and the exchange or trades that happened in the Renaissance period. So the Abbasists, no, they are kaning they make the terms. So in the 14th century were instrumental in the merchants, the new Hindu-Arabic decimal place value system, and the algorithms for using it. These Abbasists had thoroughly studied Arabic mathematics, which emphasized algebraic methods during the 14th and 15th centuries. The Abbasists extended the Islamic methods by introducing abbreviations and symbolism, so developing new methods for dealing with complex algebraic problems. So the Abbasists, no, nagbuhat na jud sila og mga term para nag-specialize sa ilahang mga pag-trade. So mao ni ang mga example. Unlike Islamic algebra, which was entirely rhetorical, the Abbasists allowed the use of symbols for announced standard. So cosa, thing; censo, square; cubo, cube; radius, root; p or payo, plus; m, meno or minus. Nicolas Cosa from 1401 to 1464. Mathematician, scholar, experimental scientist, and influential philosopher stressed the incomplete nature of man's knowledge of God and the universe. He was interested in geometry and logic. He contributed to the study of infinity, studying the infinitely large and the infinitely small. He contributed to the study of infinity, studying the infinitely large and the infinitely small. He claims that the infinity can be somehow grasped, however not accurately, in mathematics by mind with the help of concepts, but it cannot be grasped with the help of senses. Nicholas argued that infinity cannot be characterized in terms of quantity. It cannot be quantified. In fact, there is no way from quantity to infinity. Si Johann Mollier-Montaños, 1436 to 1476. At the age of 14, he entered the Vienna. He became enchanted with all things mathematical and astronomical. In a remarkable quote taken from a letter to another mathematician, we feel his total joy in mathematics and astronomy. So, nag-quote siya, I do not know whether my pen will run. It will use up all my paper if I don't stop it. One problem after another occurs to me, and there are so many beautiful ones that I hesitate as to which I should submit to you. So, in 1464, he wrote the Triangulis Omnimonis, on triangles of every kind, an early text on trigonometry in which he solved plane triangles, proved the law of sines, and gives an introduction to spherical geometry. In Tabulae Directionum, a trigonometric treatise, he furnished trigonometric tables. For his purpose, he selected R is equals to 600,000 or 10 million or 600 million It includes tangent tables with R is equal to 100,000. Example, tangent man siya. Sakto ba? 89 degrees or 5,729,796. Actual tangent 89 degrees times 100,000 is equal to 5,728,996. So Nicholas Shukey, magano ni 1445 to 1500s. A French physician, Shukey wrote tripartite science des nombres for 1484. The mathematics in tripartite was known to the Islamic algebraists, but tripartite is the first detailed algebra in French. Few details on the nature and style of this work. So tripartite 1, tripartite 2, and tripartite 3. So let's try to understand what are the tripartites. Tripartite 1. He uses the Hindu-Arabic place value system. Use the result for fractions between given a, b, c, d is greater than 0. Then a plus c over b plus d is between a over b and c over d. For example, 2 over 7 is between 1 over 2 and 1 over 5. No proof is given. He uses this to approximate roots of quadratics. So tripartite 2 uses the fraction rule to extract square roots. Find di makita da square root of 6 di makita yan 1 and open parenthesis 1 close parenthesis 2 is greater than r greater than 3. So muna yung example sa tripartite 2. Introduces some notation. P or plus or M is equal to minus. Underline for grouping. R square or square root. So R3 is cube root. So R square root 6. Square root R squared. So square root ni siya kay mo may nakabutang dre sa babaw. R square root 6 is equal to 6 square root then square root of 14p or plus. So mo ni siya ang tripartite mo ni sa French nga gibuhat ni kinsa to siya? Nicholas Shukey. So mo ni iyang tripartite number 2. R squared or square root 6 is equal to square root of 6. So R squared is square root 14 plus or p. Di ba? Plus p. R squared for square root of 180 is equal to square root of 14 plus square root of 80. So, allows negative coefficients. So, nagamit sa og mga sign niya, katong P og M. Namamani siya ang kuan sa French. Si, ano to siya? Nicholas Shukey. So, tripartite number 3 introduces exponential notation. So, 0.5, point to the power of 1. So, ano siya ang kwansad, ang iyahang tripartite number 3. So, 9x 9 second mains. So, 0.72 point to the power of 1 party par 0.8 point to the power of 3 equals 9.9.2 m. So, notes that there are multiple solutions of some systems of 2 equations in 3 unknowns. So, Luca Pacioli, 1445 to 1517. Pacioli was a teacher of some renowned, also assembled a vast collection of mathematical materials over some 20 years. Pacioli wrote Somma di Arithmetica, Geometrica Proportioni et Proportionalita, 1494. It gives a summary of the mathematics known at the time. Somma studies arithmetic algebra, geometry, and trigonometry and provided a basis for the major progress in mathematics which took place in Europe shortly after this time. Excuse me. It overshadowed Shukey's tripartite but was not mathematically significant. Subsequently, Shukey's work was scarcely mentioned. So Adam Riess, 1492 to 1559. German wrote the cos 1524, an influenced arithmetic and algebra text. For income, he wrote arithmetic textbooks, Rechnung auf der Linien, and Federn Inzal, Mais, and Gwitz of Allerley Hinderung. It contains addition, subtraction, multiplication, and division. Reyes offered methods derived from the abacus, those derived from India. Michael Stiefel, German monk turned itinerant Lutheran preacher, for a time a professor at Jena. We wrote Arithmetica Integra in 1544. It was the most important of the 16th century algebras. Used the plus and the negative. So siya day ang nagkuan ani si Michael Stiefel ang naguna gamit aning plus sign and the negative plus sign and the minus sign. Significant for treatment of negative numbers, radicals, and powers. Using negative coefficients, all the many cases of quadratics are reduced to just one, but no negative roots allowed, and the irrationals. So I'm Wilbert Baron. Sorry, na-late akong pag-introduce akong kagalingon. Then, that is all my part for this report, and I am turning over to my groupmate.
Good day, everyone. I am Christine May Islit, the second reporter of the Renaissance period. The first mathematician is the Robert Ricordi, 1510 to 1558. He is an Englishman, virtually established the English School of Mathematics, and first introduced algebra into England. The equal symbols appears in the Recorder's book, The Whetstone of White, published in 1557. He justifies using two parallel line segments because no two signs can be more equal. Yes, he invented the equal sign. The second is Girolamo Cardano, 1501 to 1576. He is famed for his work, Ars Magna, which was the first Latin theatris devoted solely to algebra. Cardano's Liber de Ludo Allel, 1563, was the first study of the theory of probability. If anything, it is remarkable for its errors as well as truths. With Tartaglia, and a century before Descartes, he considered the solution of geometric problems using algebra. Cardano is reported to have correctly predicted the exact date of his own death, on prediction made true by his own suicide. Next is Niccolò Fontana Tartaglia, 1500s and 1557. He is famed for his algebraic solution of cubic equations, which was published in Cardan's Ars Magna. Tartaglia was the first thought in mathematics, having an extraordinary ability, was able to earn his living teaching at Verona and Venice, 1534. The first person known to have solved cubic equation algebraically was Spicio del Fierro. On his deathbed, Del Fierro passed the secret to his rather poor student Antonio Maria Fior. Tartaglia then had a competition with Fior. Tartaglia, by winning the competition in 1535, he became famed as the discoverer for a formula to solve cubic equations, because negative numbers were not used and not even recognized. There was more than one type of cubic equation, and Tartaglia could solve all types. Fior could solve only one type. That's the difference. Tartaglia wrote Nova Scientia, 1537, a new science. On the application of mathematics to artillery fire, he discovered new ballistic methods and instruments, including the first firing tables. Tartaglia also wrote a popular arithmetic text, Trattato di Numeri et Misure, in 3 volumes, 1556 to 60. Treatise on Numbers and Measures, an encyclopedic treatment of elementary mathematics. He was also the first Italian translator and publisher of Euclid's Elements in 1543. The next mathematician is Ludovico Ferrari, 1522 to 1565. He was orphaned at the age of 14. having no formal education. He was sent as the refuge of Milan, where he joined the household of Girolamo Cardano in 1536. Cardano introduced him to Latin, Greek, and mathematics, a not normal course of training for an errand boy. He collaborated with Cardano in researches on the cubic and quartic equation, the result of which were published the Ars Magna in 1545. Indeed, by all accounts, it was Ferrari who found the method of solving the quartic equation. The last is Scipion dal Fierro, 1465 to 1525, the first to solve the cubic equation by radicals. He only solved one of the two cases. The fact that zero and negative numbers were not in use made any distinct cases. He kept his discovery secret and only told his student Fior shortly before his death. Ferrari reports seeing a notebook in Del Fierro's handwriting where the solution is clearly written down. The algorithm for the solution of the cubic. For the solution of the cubic requires a canonical form for the cubic, and this requires a preliminary transformation. Transformation ax to the power of 3 plus bx to the power of 2 and cx equals d into x to the power of 3 plus px and q. First, dividing a and then using the transformation x equals y plus b and then y equals x. The next is define u and v by u minus v equals x and uv equals 1, 3, p. This gives the equation which is quantity u minus v to the power of 3 plus p quantity u minus v equals q. Then u to the power of 3 minus 3u to the power of 3v plus 3uv to the power of 2 minus v3 plus p quantity of u minus v equals q. Then we are here that u to the power of 3 minus v to the power of 3 minus 3uv quantity of u minus v plus p quantity u minus v equals q. Then we arrive this equation u to the power of 3 minus v to the power of 3 equals q. Using v equals p over 3, u substitute to get u to the power of 3 over p to the power of 3. Then u to the power of 3 equals q. U to the power of 6 minus q u to the power of 3 equals p over 3 to the power of 3. So, we have here the u to the power of 3, quantity of to the power of 2 minus q to the quantity of the power of 3 equals p over 3 to the power of 3. Then solve for u. Here is the u equals the quantity of a, positive negative square root of a to the second power plus 4 quantity of p over 3 to the third power over 2 and then divided by 1 over 3. And then for v, finally for x, now compute v negative p minus 3 u and then compute x equals u minus v. After some simplification, we obtain the form given by Cardano, namely, we have here another formula. X equals to the power of 3 square root of p over 3 to the power of 3 plus a over 2 to the power of 2 plus q over 2 minus 3 to the power square root of p over 3 to the power of 3 plus a minus a over 2 to the power of 2 minus q over 2. However, his solution is rhetorical. Solve x to the power of 3 plus 3 times equals 4. So we have here the x equals quantity of the square root of 1 plus 4 plus 2 quantity of 1 over 3 minus quantity of square root of 1 plus 4 minus 2 quantity of 1 over 3. Therefore, we arrive the equation quantity of square root of 5 plus 2 quantity of 1 over 3 minus quantity square root of 5 minus 2 then quantity of 1 over 3. Therefore, we arrive the answers 1. In Ars Magna, we find x to the power of 3 equals 15x plus 4. The solution here by the formula is x equals to the power of 3 square root of 2 plus square root of negative 121 plus to the power of 3 square root of 2 minus square root of negative 121. Cardano knew there was no square root of negative 121, and he knew also x equals 4 was a solution. He did not know to proceed. He referred to such square roots as sophist, and through taking square roots of negative numbers was a subtitle as it is useless. However, from this example, Raphael Bombelli, ca. 1526 to 1573, made the first step toward complex numbers. Bombelli's idea was that the radicals themselves might be related in much the way that the radicands can relate. In fact, notice that the terms square root of the power of 3 is square root of 2 plus square root of negative 121 equals 2 minus 11, and to the power of 3 square root of 2 minus square root of negative 121 equals 2 minus 11 are complex conjugates. Therefore, it is reasonable to assume that the first of them has the form 2 plus ib. If 2 plus ib equals 3 square root of 2 11i, then it is a simple calculation to show that b equals 1. Thus, we arrive 2 plus I equals square root of 2 plus 11i to the power of 3. Then 2 minus I equals 3 square root of 2 minus 11i. Hence, the root of the cubic is x equals 2 plus 1 square root of negative 1 plus 2 minus 1 square root of negative 1 equals 4. What is remarkable is that Bombelli had not the slightest idea of complex numbers, except some vague intuition that the form might be invariant under algebraic operations. Cardano also posed the problem with complex roots. Here are the x plus y equals 10, and then xy equals 40. X equals 5 plus square root of negative 15, and y equals 5 minus square root of negative 15. That's all. Thank you.
The Super Magic Square. It is a tribute to the respect in which mathematics was held in Renaissance Europe that the famed German artist Albrecht Dürer included an order of negative form a minus 4 order 4 magic squares in his engraving Melancholia 1. In fact, it is a so-called super magic square, with many more lines of addition symmetry than a regular 4 by 4 magic square. The year of the work, 1514, is shown in the two bottom central squares, which is shown in the right side, the super magic square. Not only do the rows, columns, and diagonals add up to 34, but so do all the combinations of 4 numbers marked by linked dots in the squares below. During the 16th and early 17th century, the equals, multiplication, divisions, radical or root, decimal, and inequality symbols gradually introduced and standardized. The use of decimal fractions and decimal arithmetic is usually attributed to the Flemish mathematician Simon Stevin, the late 16th century, although this decimal point notation was not popularized until early in the 17th century. Plus and minus by Johanni Widman on 1489, Luca Pacioli on 1494, Gilles van der Hoeke on 1514. The multiplication, which was discovered by William Othard on 1631 or 1618, and the dot, which indicates multiplication, was discovered by Gottfried Leibniz on 1698 and Johann Bernoulli on 1694. The division, which was discovered by Johann Rahn on 1659 and Johann Pale on 1668. The equal sign, which was discovered by Robert Ricordi on 1557 and William Othard on 1618. The less than and the greater than by Thomas Harriot on 1631. The exponent, which was introduced by Nicolas Chuquet, Pierre Hérigon on 1634, René Descartes on 1637. The radical or root by Christophe Rodolphe on 1525, Albert Girard on 1629, René Descartes on 1637. Fraction bar by Fibonacci on 1202. The decimal point by Francisco Pelos on 1492, Mageni on 1592, Bartholomeus Pitiscos on 1595, and John Napier on 1617. In the wake of the Renaissance, the 17th century saw an unprecedented explosion of mathematical scientific across Europe, a period sometimes called the Age of Reason. The invention of the logarithm in the early 17th century by John Napier and early improved by Napier and Henry Briggs contributed to the advance of science, astronomy, and mathematics by making some difficult calculations relatively easy. It was one of the most significant mathematical development of the age, and 17th century physicists like Kepler and Newton could never have performed the complex calculation needed for their innovations without it. The French astronomer and mathematician Pierre-Simon Laplace remarked almost 2 centuries later that Napier, by halving the labors of astronomers, had doubled their lifetimes. The common bases of logarithms are 10 and e, although their bases are also possible. The log of 1 in any base is always 0. The log 10 of 10 is 1 because 10 to the power of 1 is 10. And likewise, the log e of 2.77128 is 1, as shown in the graph below by John Napier on early 17th century. Although base 10 is the most popular base, another common base of logarithms is the number e, which has a value of 2.7182818, and which is special properties which make it very useful for logarithmic calculations. These are known as the natural logarithms and are written log over e or in. Briggs produced extensive lookup tables of common or base 10 logarithms, and by 1622, William Othard had produced a logarithmic slide rule, an instrument which became indispensable in technological innovation for the next 300 years. Napier also improved Simon Stevens' decimal notation and popularized the use of decimal point, and made lattice multiplication more convenient with the introduction of Napier's bonus, a multiplication tool using a set of numbered rods. Marine Mersenne, largely remembered in mathematics today in the di makilaro. Mersenne prime numbers that are 1 less than a power of 2. Example, 3 quantity of 2 squared minus 1 is quantity 7, quantity 2 cubed minus 1, quantity 31, quantity of 2 to the power of 5 minus 1, quantity 127, quantity to the power of 7 out 2 to the power of 7 minus 1, quantity 8191, quantity of 2 to the power of 13 minus 1, etc. In modern times, the largest known prime number has almost always been a Mersenne prime, but in actual fact, Mersenne's real connection with the numbers was only to compile a none-too-accurate list of smaller ones. This is the graph of the numbers of digits in the known Mersenne prime numbers. Note that the vertical scale is logarithmic, as shown in the graph below. René Descartes, sometimes considered the first of the modern of mathematics. His development of analytic geometry and Cartesian coordinates in the mid-17th century soon allowed the orbits of the planets to be plotted on a graph, as well as laying the foundations for the later development of calculus and much later multidimensional geometry. Two other great French mathematicians were close contemporaries of Descartes. This is Pierre de Fermat and Blaise Pascal. Fermat formulated several theorems which greatly extended our knowledge of number theory, as well as contributing some works on infinitesimal calculus. Pascal is most famous for Pascal's triangle of binomial coefficients, although similar figures had actually been produced by Chinese and Persian mathematicians long before him. It was an ongoing exchange of letters between Fermat and Pascal that led to the development of the concept of expected values in the field of probability theory. The first published work on probability theory, however, and the first to outline the concept of mathematical expectation was by the Dutchman Christian Huygens in 1657, although it was largely based on the ideas in the letters of the two Frenchmen. Gerard Desargues, considered one of the founders of the field of projective geometry, later developed further by Jean-Victor Poncelet and Gaspard Monge. Projective geometry considers what happens to shapes when they are projected onto a non-parallel plane. Desargues developed the pivotal concept of the point at infinity, where parallel actually meet. His perspective theorem states that when two triangles are in perspective, their corresponding sides meet at points on the same collinear line. This is Desargues' perspective theorem. Isaac Newton was able to pin down the laws of physics in an unprecedented way, and he effectively laid the groundwork for all of classical mechanics almost single-handedly. But his contribution to mathematics should never be underestimated, and nowadays he is often considered, along with Archimedes and Gauss, as one of the greatest mathematicians of all time. Newton and independently the German philosopher and mathematician Gottfried Leibniz completely revolutionized mathematics by the development of infinitesimal calculus with its two main operations, differentiation and integration. Oh. Thank you for listening. That is all for our report about the Renaissance period of history of mathematics. This is Vince Romero. Sorry for the late introduction. Thank you, sir.